People sometimes ask me, well, how did you get into chemistry? By accident. At 15 years old in high school, there wasn't any chemistry in my class. But then the head teacher changed, and the new one was a physicist. He brought in organic chemistry. And I said, I'd like to do organic chemistry. And the school said, Burgess, you're just dirt. Your dad is just a plumber. We don't have enough room. You go and do art. So I said, you're right. And I went and did art for 3 months. On the last day of class, Mr. Bradnock, my art teacher, lovely man, I love what he did for me. He gave us all a piece of clay. And he said, make anything out of this, anything you like. You got an hour. So I sat there for an hour, massaging this piece of clay, trying to make something creative from it. And at the end of class, I went to Mr. Bradnock and I showed him my pot, and it looked awful. And I said to him, Mr. Bradnock, sir, I'd like to do chemistry. He took me straight down to the chemistry class. That's how I got into chemistry. But why did I stick with it? That's a slightly different story. You see, organic chemistry is the study of C, H, N, and O. Why are C, H, N, and O so special? And to know the answer to that, we've got to look at bonding a little bit. There's something distinct about bonding between carbon. Carbon, quite uniquely, can form long chains, and these can be branched. They can double back on themselves to form rings. Why is carbon so special? Why can it do this? This is the periodic table. There's a lot of elements there. Why is carbon special? Well, let's zoom in on carbon and its nearest neighbors. They're the elements that are most likely to be like carbon: boron, aluminium, silicon, phosphorus, nitrogen, oxygen, and sulfur. But really, carbon stands out. It stands out because it can bond so nicely with N, O, and some of these other elements as well. But none of those can form chains and bond to the others with as much variety. Now, why is that? Let's look at boron, for instance. Boron has 3 electrons in its outer shell. Sure enough, it can bond with 3 hydrogen atoms. That gives the molecule BH3. But BH3 only has 6 electrons in the outer shell, 3 from the hydrogens, 3 from the boron. Why don't we add 4 hydrogens? So if we did, we approach with another hydrogen atom, that would be BH4 dot, 7 electrons. That's not stable. Okay, what about if we approach with H minus? That's a proton with 2 electrons around it. That gives us BH4 minus that can't form rings and chains. Well, what about nitrogen? We know that nitrogen can form an NN single bond. That's hydrazine, derivative of ammonia. But if I try to draw 3 hydrogens in a row, it kind of makes sense, but I don't think I've ever seen that molecule. It's very unstable because dinitrogen, N triple bond N, is so stable. It will decompose explosively. Similarly, oxygen. Oxygen can form OO single bonds, hydrogen peroxide. Oxygen can form OOO in an arrangement called ozone. That's the smell that you get at the seaside. But if we try to make O4, certainly it would decompose to dioxygen. It's unstable. It cannot form chains. Sulfur can form chains, but it's boring. They don't do that much. Elemental sulfur is full of chains, but you can burn it. You can add oxygen, maybe you can add nitrogen, but really only the SS single bond is useful in nature. The second thing that's special about carbon is it can form multiple bonds. It can form alkenes, it can form alkynes. Those double bonds can be in a chain with single bonds. They can be in the middle of a chain. They can be in a ring. This gives you an infinite amount of diversity. Well, why does carbon bond to itself to give a double bond? Well, let's imagine a CH2 fragment. Do an inventory of the electrons. We've got 4 from carbon. We loan 2 from the 2 hydrogens. That's 6 electrons. We haven't reached the stable octet yet. But if we take 2 CH2 fragments together, the 2 electrons on each carbon that are not bonded to the hydrogens share in two bonds, a double bond. Can we only do this with carbon? No, we can do it with nitrogen as well. Nitrogen, H, NH fragment. If it approaches the CH2, NH has 4 electrons. It donates one to share with the hydrogen in an NH bond, 4 left over. It uses 2 of those to share with the carbon, and we form a CN double bond. And there's a lone pair left on the nitrogen. What about oxygen? Same type of story. Oxygen has 6 electrons. If we bring that close to the CH2, it can use 2 of them to form a CO double bond, and there's 2 lone pairs left on oxygen. How about CH fragments? Oh, well, let's add up the electrons again. The carbon has 3 electrons left over when it shares 1 with the hydrogen, and it needs 8. 2 CH fragments bind together. They share between them 3 electrons each. That forms 3 bonds holding 2 electrons each, and we form ethine or acetylene. And can we combine that CH fragment with nitrogen? Yes, the CH needs 3 electrons. It gets 3 electrons from the nitrogen, leaving 1 lone pair, and we form a C and triple bond. So that's why CH and N are special. So what do we get from combining CH and N? Well, we get a lot of interesting things. We get molecules like adenosine. And of course, if you've eaten anything recently, you're forming ATP, without which your cells cannot survive. Metabolism. Adenosine is also a component of RNA and in its deoxygenated form of DNA, and that's responsible for the construction of proteins. Proteins are made of amino acids like histidine and tryptophan, combinations of C, H, N, and O. Ribose is cyclized in RNA and DNA. And of course, ribose is a carbohydrate. Carbohydrates do lots of things in the body. Like, for instance, glucose is a source of energy. And sucrose is a disaccharide. It's got 2 carbohydrate fragments put together. If you eat too much of that, you start forming fats, lipids. Lipids can be transformed into molecules like cholesterol. And of course, if your cholesterol goes high, you get heart disease. Lipids can be transformed into hormones that distinguish men and women, testosterone and estradiol. Organic chemistry isn't boring. Organic chemistry is the wonderful combination of C, H, N, and O to give us life. Sure, there's parts of organic chemistry which are dead. They only exist in a synthetic world. But the really interesting ones are the basis for all of biology, molecular biology, virology. All these subjects are derived from organic chemistry. And that's why it's so fascinating to me. Thank you for listening. Bye-bye.